All right, so again, it's proved that the limit exists and specifically is equal to 0. So you know going into the problem that the limit ought to be equal to 0. So if you get anything other than 0, then you know that you're kind of barking up the wrong tree. Right? So that's kind of where we're at. So the big question, really the big question, is going to be, how can we build an inequality from this expression, from this whole shebang here, this guy, all of this stuff? How can I build an inequality from that so that I can actually find the limit of the outer fringes of that inequality, that compound inequality, and therefore come up with the limit of the whole thing? Okay, so the best way of handling it is to just really look at the denominator. So we can look at just 1 over x minus 1 squared plus y squared. Okay, kind of thinking of that as sort of like a parent function. And we want to kind of trap that in between two other functions. So we just go back to what I talked about last class, and that is this idea that if a denominator is smaller in a fraction in which the numerator is 1, if the denominator is smaller, then the overall fraction value is larger. All right. So what I would want to do is make the denominator smaller somehow. And I can do that by just getting rid of part of the sum. I know, for example, that 1 over x minus 1 squared one is getting divided by less here than it is in this original fraction. So that means that this fraction here has to be greater than or equal to the other fraction, right? And so what we were saying last time is that we know now that we have a bound on the high side. If we negate it, we would have a natural bound on the low side. Right? So and then I'm just going to copy and negate it. And then once we do that, we can go through and multiply by whatever the numerator is. That pop-up is going to happen repeatedly. Fortunately, I don't know why it's happening. But I'm going to multiply the entire compound inequality by x minus 1 squared times the natural log of x. All right, so that's getting, so this whole thing, this whole compound inequality is getting multiplied by that expression, right? And so that gives us negative ln of x is less than or equal to, I can't even write, x minus 1 squared ln of x all over that denominator. And that in turn would be less than or equal to just a plain old ln of x. And so what I would then do is apply the limit, and that is the limit as xy is approaching 1, 0. That's applying to each part. Okay, so see if I can do this in a halfway efficient sort of manner. So we're taking the limit of that. Then the limit of this, which is ultimately what we're looking for. And then the limit of this. I'm going to do a little resize. Bring it in. So there is no y term in my outer expression, right, in either of them. So I'm really just evaluating this for when x is equal to 1 in both cases. The natural log of 1 is equal to 0, regardless of whether it's positive or negative. So 0 less than or equal to the inner component, which is in turn less than or equal to 0. Which therefore means that the entire limit is in fact equal to 0. Right. So, for this kind of problem, I don't think it's overly challenging. It's more kind of a pain to write it all out. Right? So once you get the writing part handled, the challenge, it kind of disappears. Right. For me, it's the digital inking. That's my compromise. It's like, it's not that bad as long as I can copy paste the living daylights out of it. But if I had to write this all out, I would not be happy. So sorry if you have to write it all out. I would not want to be you. Nah. Some of you are already doing the digital inking, which is really good. Like whatever app you like. I mean, there's plenty of apps out there that allow you to annotate. You don't have to use GoodNotes. You can use whatever you want. Just find something that works on your device that allows you to annotate PDFs. It does in a lot of ways make your life a lot easier. And some of these apps are not expensive, and some of them are free. But I found the preview ones. I'm sorry, the free ones that I previewed have not been very good. So you might have to spend a few bucks. But just a thought. Anyway, I can't remember. I don't think I pointed out this typo. This little stray F here. Pretty terrible looking. Should be all on one line. And it's a little reformat job necessary there. So continuity of a function of two variables. If the limit of the function exists, so that's the number one necessity. The limit has to exist and specifically be equal to a particular point from all directions. Then we would say that the function of multiple variables is continuous. Right? It kind of goes back to in Calc 1, or even when we talk about it with vector value functions, the first thing you have to do is verify that there was a point at that particular location that was also the location that the limit was approaching from both directions. Right? It's just in this case, there has to be a point there, but from all directions, we have to be aiming for that point. Right? So it's just like in Calc 1, it's a whole lot easier to see where a function is discontinuous than it is to see where it is continuous. Right? So once you do that, find any points of discontinuity, you remove it from the domain, and then what you're left with is an assumption that the remaining points are the points in which the function is continuous. Right? So looking at number 7, find all the points where it's continuous. We have x over x squared minus y. Right? So first thing I would want to do is figure out where this function is undefined. Right? So it's undefined when x squared minus y is equal to 0. All right. So that gives you a relation, y equals x squared. So anything along that path is going to cause this function to be undefined, which would be a location, a set of locations, a series of infinite locations where it's not defined. Right? In which case it would not be continuous at those locations because it would fail to exist. All right. So what I did was I put the original multivariable function here. That's this whole thing. And then I put the path of points for which it would not be defined. All right. So that's all accounted for now. All right. So we just have to really just kind of verify that this is in fact the case. I mean, we know it's definitely going to play out that way, but all we would need to do is just kind of make a statement saying that this is where it would not be continuous, right? But if we wanted to actually prove it, it's a little bit more of a journey. I mean, it's not really the question that's being asked though, right? So, you know, that's kind of like a specific instance. Yeah. So what we could do is make a statement saying that the function is continuous for or on the interval. Well, really, if we're using set notation, x, y, such that y cannot be equal to x squared. All right, so we're just stating the condition for which it would be continuous, which is eliminating the case where it would fail to be continuous. Okay, so you know, there's plenty of different ways that you can verify that the limit would not exist at that location. You know, I just want to verify before I waste too much time. And I'm pretty sure this is one that we did not do. Okay, so what you can do is you can actually just kind of pick a point that follows this path and show that the limit doesn't exist at that location. You know, just as a quick example, it's not like I said, it's not necessary for this problem, but I did want to take a minute and show you how that would look. So it's kind of a cool relationship. It's purely academic. I'm just going to resize a smidge. So we'd be looking at, like, for example, we could evaluate the function f of, let's say, well, anything that follows that path. I could say f of 1, 1. Right? Because that would follow that path. F of 1, 1. If I just plug it in, I get 1 over 1 squared minus 1, which is 1 over 0 undefined. Right? I could also, if I wanted to, find the limit as xy approaches 1, 1. And that's specifically, again, for the function x over x squared minus y, which would amount to the same computation, so still giving the 1 over 0. All right, that's a particular case. But what I could also do is change my variables. So for example, if I wanted to, I could let x equal t and y equal t squared and write the function as f of t, which would be t over t squared minus t squared. Okay, so that would be t over 0. All right, so unless t is equal to 0 itself, this would be an instance in which the limit did not exist. Right? I mean, I'd have to craft it as a limit, but still, you know, that would be perfectly fine. You know, so I would be saying something like the limit as t approaches a of t over 0 does not exist. Right? So that'd be kind of like a mini proof. You know, so one case would be, you know, a numerical justification. Another case would be kind of like more along the lines of a rigorous proof. But like I said, this question was only asking for this stuff. I was just kind of taking it upon myself to show you a little bit more detail related to it, if you needed to ever prove anything. What if x and y are 0? if X and Y are equal, well, that would be a true, oh, then it's indeterminate. So then in that case, we'd have to go back to a solution along these lines. So where you'd have to make the assumption if X and Y are approaching 0, then you'd have to show that not all pathways ended up giving you the same limit. All right, so you'd still get there, because if they're both 0, you're going to get 0 over 0, which is indeterminate. So in that instance, you'd have to go a little bit further and show the more detail, using the parametric method that we talked about last class. So that's definitely an extension to this kind of concept that kind of takes some doing. But good question. So we're going to hop on up to page 46. Compute all 4 second-order partial derivatives for the cosine sine minus the exponential e to the xy. It's an interesting problem. It definitely, you know just by looking at it that you're in for an adventure, in coming up with the solution to this kind of question. Because it wasn't really explicitly stated here like it was in the previous question, where you had to find the first order partial for number 1, and then on number 2 you use that to come up with at least some of the second order partials. Here it's implied that if you're going to come up with a second order partial, you need to first come up with the first order partial. So that's what we're going to do. Recommendation, just so you don't go too crazy with the delta notation, just use the lowercase f subscript of x to represent the first order partial, and then do the same thing for the y's. And I think it ends up being a little bit easier that way. Right, but we're going to treat the x as the variable and the y as the constant or constant multiplier. Right. So we're looking at, if I'm doing this with respect to x, any instance involving the x only, I need that to be a little bit smaller, is going to be treated as the variable. So sine of y is actually just it's just going to act as a coefficient. So bring that along for the ride. And then I just take the derivative of cosine of x, which is negative sine of x. So negative, that's poor quality negative, negative sine of x. Right. Then the other piece, it's e to the xy. All right. So e to the xy, when we take the derivative of exponential e, we keep it as is, and you multiply by the derivative of the exponent. All right. So the derivative of xy, assuming that y is a constant multiple of x, we hang on to the y, take the derivative of the x, which is going to go to 1. All right, you don't really have to write the 1. I'm just doing it so I can kind of highlight the appropriate part here. So this is now negative, I'll clean it up a little bit, sine x sine y minus y e to the xy. So we'll do the same thing for f sub y, this time differentiating with respect to y, which means that anything that doesn't contain a y is going to be thought of as constant. Right? So in the case of cosine x sine y, cosine x comes along for the ride. Sine y has the derivative of cosine of y. Minus, same idea for exponential e, rewrite it as is, and multiply by the derivative of the exponent. If y is the variable and x is the coefficient, then the derivative would be x times it would be x times the derivative of y with respect to y, which would be 1. All right. So it's essentially, for at least that part, the same idea, except we get an x instead of a y. All right. So cosine x cosine y minus x e to the xy. All right. So now I need my second order partials. Now the good news is just going through the original function as well as the first order partials, we're looking at functions that are everywhere continuous. And, you know, that's easier said than, well, actually easier said than that doesn't make sense there, but it's easy for me to say that. You know, like, oh, you made the problem, or you got the answer, whatever. It's really not like that. It's more like sine functions are continuous on negative infinity to infinity, and so are exponential functions. Right? These functions would not have any restrictions. Right? So that's great news, because what that tells me is that my mixed second order partial is going to be the same, whether it's f sub xy or f sub yx. So when it says compute all 4 second order partials, I really only need 3. Right? In the grand scheme of things, it's still a ton of work that we have to do, but it's like a little bit less than, you know, maybe it's not as bad. Right? So f sub xx So now I'm going to take the derivative of this expression with respect to x. All right. So the derivative of sine of x is cosine x, everything else comes along for the ride. So negative cosine x sine y. All right, everything else just got transported along for the ride. Now, it's kind of a nice development here, although it's not always going to play out this way. Even in this problem, we're going to come to an instance where this part of it is going to be kind of a pain. But for now, it's not bad, because x is the only variable here. Everything else is treated as a constant or a constant multiple. All right, so that negative y is a constant multiple of e to the xy, so it just comes along for the ride. E to the xy has a derivative of e to the xy, and then I multiply by the derivative with respect to x, which I've already kind of played out. We've done that before. That was right up here, we did that. So the derivative there would be times y times 1. Again, you don't have to write the times 1. I'm just doing it so I can highlight. All right. So I can clean this up if I want to. There's really no value in doing that, just because I'm not taking the third derivative, at least not yet. So, but you know, like sometimes we can't resist. The negative cosine x sine y minus, and in the grand scheme of things, which apparently is one of my favorite things to say, I don't know why. There really isn't much to simplify, so you might as well. Now, then when I'm looking for my mixed second order partial, I'm taking this expression and I'm differentiating it now with respect to y. If you're going to get confused in this process, it's probably going to be in this kind of, you know, context, right? So any instance in which there's a y is now treated as a variable. All right. So for the sine x sine y part, that's okay. The derivative of sine of y is cosine of y. Everything else comes along for the ride. So negative sine x cosine y. All right. But then now I'm looking at this part here. I'm just going to kind of smidge it over, which is now really the product of two functions, each containing a y. Y is not a constant anymore, it's a variable. Since I have two variable functions, I now have to treat it like I would any other problem in which I have two functions that are being multiplied together. Right? And that would be, it's a product, so I have to use the product. Right? So minus the first function, y, times the derivative of the second function, e to the xy, multiplied by the derivative of the exponent, which now the variable is y. So it's going to be multiplied. So we hang on to the x, take the derivative of the y, Let me highlight the appropriate piece. Plus the second function, e to the xy, times the derivative of the first function, derivative of that y is just another 1. Right. So again, it might be something that you look at and say, well, I can clean this up a little bit. But again, if you don't have a reason to, don't go too crazy. Sine x cosine y minus, you can leave it in parentheses if you want. I see a common e to the xy, you can factor it out. If it turns out that that's something you need to do, then by all means. So the question is, why does the y remain? I suppose it depends on which y you're talking about. Is it this y? I think it might be this y. Because if tan, oh, right, okay. So that y is related to the product rule. So what we did was we took the first function. This is my first function, and this is my second function. So here's the first times the derivative of the second. That's all of this stuff. Plus the second function times the derivative of the first. So in the housekeeping part of the process, I can clean things up a smidge, but not really too much. Maybe I'll distribute the negative, I guess. You know, make it look a little nicer. So I could say xy e to the xy minus another e to the xy. But really, beyond that, there isn't much else to do, not without some kind of context provided. Right. So we now have, well, it seems like we only have half the work needed to compute all 4 second order partials, but really we now know that this is going to be the same as f sub yx. All right. So this is also f sub yx. All right. So now we have 3/4 of the work done. So then the only thing that remains is computing f sub y, which is actually going to be not too bad. I'm just going to move this down a little bit. So I can tuck the f sub y right here. So again, I'm taking the derivative with respect to y. So any instance involving a y is considered variable. Everything else is considered constant or a constant multiple. So derivative of cosine y is negative sine. So I'm bringing the cosine x down for a ride. That negative and the sine y is attributed to the cosine of y. Minus x is now treated as a constant multiple of e to the xy, which is good news. So x e to the xy multiplied by the derivative of xy. Again, the x is the constant multiple of y. So that comes along for the ride, multiplied by the derivative of the y, which is a 1. So then if we were to clean this up, there isn't any more to clean up here than there was for the f sub xx, which would be negative cosine x sine y minus x squared e to the xy. Right. And so that leaves all of this stuff to be the mixed second order partials. Right. So they amount to the same thing. But that's only because we're dealing with continuous functions. Right. If there were discontinuities along the way, that would be a different story, and it's a different bridge that we'll have to cross down the line. Right. So, and there's ways to handle that to make it more convenient, but different problem for a different day. But yeah, there's a lot of heavy lifting in these kind of problems. I mean, if you look at what we did for number 2, even that was, I mean, that was polynomial based, and that was still a ride. you know. So it's just it. I would say it's not. I don't want to oversimplify things because I say things aren't hard, but there. I'm sure there are people that are like, "What are you talking about, dude? This is killer." You know, I mean, I don't want to go down that road too much, but you know, conceptually, it's not too bad. It's just there's so many little tiny details to lose track of that people get this stuff wrong, myself included, all the time, just because like halfway through a problem, you just lose track of which variable you're working with. Wait, am I working with cosine? I'm sorry, x or y? I totally forgot. And then, like midstream, you switch over and you start differentiating with respect to x as opposed to y, or vice versa. That's the kind of stuff you need to be careful about when it comes to partial derivatives or integrals. Right, when we get to integrals. Right. So on the next page, you see here. Now I'm just being mean here. It's the same function, but it's saying find x, f sub x, y, x, and then f sub x, y, x, y, right? So it's saying just go the next level and then the level after that. So I really am going to take the mixed second order partial stuff, grab that. And I don't know if anybody noticed it, but as I was kind of shifted gears midstream, where I was like, don't even bother simplifying it unless you really need to. So at first I wasn't even going to simplify it. Then in a moment of clarity, I remembered that I had this problem in here where it built off of that. So, it's a good thing we did simplify it because we'd have to do it anyway. Right. So this is our f sub xy. Now we need f sub xy x. So this is the third order partial. Now, if I wanted f sub xy x, f sub x xy, f sub y x x, they're all going to be the same thing. All right. So that's something to keep in mind. And I'll clarify that in writing in a couple of minutes. But for now, we're taking the derivative where the variable is x. Right. And at first glance, so very funny, like it looks like it would be kind of a beast, but it's actually not that bad, only because we did simplify it a little bit, right? So sine has a derivative of cosine, so this is negative cosine x cosine y. The variable x only exists in that second piece, in that one location. Everything else is the constant multiplier of that. So all that constant multiple stuff comes along for the ride, y e to the y. The derivative of x goes to 1. And then the e to the xy, I mean, we've kind of beaten this to death a little bit. E to the xy has a derivative of e to the xy times, the derivative of xy, where x is the variable, is going to be y multiplied by 1. So it cleans up just a little bit. To that expression, and you see here that the cosine and sine part of it, the trig part of it, really hasn't been that bad. The thing that kind of fluctuates in terms of difficulty has been the exponential part. X, y, e to the y should be x, y, e to the x. Oh, did I screw up? Oh, dang it. Yeah, you're right. I miswrote it. You know what? I see what happened here. When I copy pasted it, I blew it. I even lost an E along the way. I don't know what the hell happened. So let me fix that. Well, first, let me make sure I wrote it right on the previous page. Yeah. Oh, you know what happened? When I started deleting stuff to clean it up, I didn't clean it up the right way. Apologies. Maybe we're gonna have this for reference here. Yeah, it just flat out lost an E. So then that, okay. And then the next step, I just lost the next. Oh, you know what happened? And then I closed up the gap, assuming that I just wrote it wrong or something. I don't know. Yeah, it was like this, and I moved it over. Ay, ay, ay. Ay, 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 ay. Let me just make sure. So I'm going to have to change my derivative in a second. I'll get to that, which really sucks because it was so much easier this way. But I just want to make sure that I wrote it correctly. All right, it looks right now. All right, so let me get rid of this stuff now. So the first part, well, the first part was good. All right, so, ay, ay, ay. So I have the variable x that's present in two different locations now. All right, so that y is a constant multiplier, but we are stuck with the product rule here. All right, so what we're going to do is smidge this over a little bit. Now, a thought before I get too far down the road. That thought involves perhaps a little bit of factoring. So if I pull out a negative e to the xy, I would have an xy minus xy plus 1. It would still be a case where you'd have to use the product rule, but it might be a little bit easier to see, you know, because then you look at this really as the product of the e to the xy, and then this separate function here. This would be my first function, and this would be my second function. It might be better that way, not because it's going to make the problem any shorter, but it might just be easier to see the solution, you know, and maybe not even that, more so like avoid any kind of mistakes due to like your mind playing tricks on you. All right, so the first function, I'm going to leave the negative out of it, e to the xy times the derivative of the second, which is a little easier to find now, all right, because the variable is x. So that means that xy is going to just a y, because x is going to 1, y comes along for the ride. So first times the derivative of the second, and the 1 goes to 0. So this would be times just a y, right? Plus the second times the derivative of the first with respect to x, which would be e to the xy, times the derivative of xy with respect to x, which is just a y. All right. I don't know, maybe that's a little easier. And we still have that, actually I was going to say we still have that e to the xy, but that's now accounted for. So you may look at this and say, well, it doesn't look any easier, but it might be. Some instance, there's some universe where this might be a little easier. There's a common y e to the xy that can be factored out. So when we're simplifying it, maybe that'll help. Because that would leave us with just well, this would go to a 1. And then this would be the only thing left over here, xy plus another 1. So negative cosine x, cosine y, minus y e to the xy, and then 2 plus xy. You might disagree. Might feel like it was easier the other way, like in the expanded form. I just knew that we were in for a little bit of a ride with that, the xy e to the xy. It would have involved product rule one way or the other, so why not? So this result, so this is an important realization here, that f sub xy, I'm sorry, f sub xyx is going to be equal to, we have a bunch of possibilities here. It's really any arrangement of the letters x and y. So f sub x, x, y, f sub y, x, x. And I think that's it, because it's, yeah, because everything else would be just transposing x's. So it's really the combination, not so much the permutations. Right? But I'm just trying to think. Yeah, because I mean, technically there would be 6 possible arrangements here, but these are all going to be equivalent to one another. But what happens is, if you get into in a purely probability kind of sense, we tend to think of this as a different x than this one. So we would say there's one here, there's one there, there's one here, there's one there. But then we could also say that we can actually swap this x with this one, and this x with this one, and this x with that one, giving you f sub x2, y, x1, but that contextually doesn't make sense. We wouldn't take a second x derivative before we take the first x derivative, right? So if you have, what I just said doesn't really have a lot of meaning for people who don't really have a lot of experience with statistics, probability, and stuff like that, combinatorics. But if you do, you might be wondering, like why the other arrangements would disappear. That would be the justification, right? So when we get to the next level, which is f sub xy, xy, what I'm really saying here is, it doesn't matter in what order you take the fourth derivative, as long as in the process you've taken the derivative with respect to x twice and the derivative with respect to y twice, right? Because this one here is going to be the same as f sub x, x, y, y, f sub y, x, y, x, f sub y, y, x, x, f sub, let's see, we could bookend it, y, x, x, y. We can go the other way. Let's see, there's 1, 2, 3, 4, 5, and the one that they gave us was 6. 4c2 is equal to 6. So that should be it, unless I'm missing some. But what we can get out of this is, wait a minute, it might be easier. Like they're saying, find f sub x, y, x, y. But maybe it's easier to work off of f sub x, x and take the derivative with respect to y twice. Or maybe take our answer for f sub y and take the derivative with respect to x twice after that. We already came this far with this, so you may look at it and say, well, I don't want to take 2 more derivatives. I just want to do it the one more time. But you could go down that road. And so with that in mind, what we could have done here is we could have done f sub xxy instead of what we did here. So we could have worked off what we found as our second order partial, the homogeneous partial, not the mixed one, and then taking the derivative of that with respect to y. So you got a lot of different pathways here, but since we had to do the work anyway, it really doesn't matter. We had to figure out all 4 second order partials. But if a question just said, here's f of x comma y, here's your original multivariable function, now figure out f sub x, y, x, y, you might say, okay, well, I'm not going to do that. What I'll do instead, because they're continuous, is I'll figure out f sub x, x, then y, y, and make my life a little bit easier. Right? It's a pathway to a more efficient solution. Right? But like I said, since we already had to build up to a solution here where we had to do all the previous steps, it really doesn't matter which way we go. So I'm just going to do x, y, x, y. So I'm differentiating here with now respect to y. So again, it's a disaster in terms of what we have to do. However, algebraically, there might be some value in maybe moving some things around. Right. So I'm looking at this and I'm saying, all right, any instance in which there's an x would be a constant multiple. I'm not in love with this piece here because I see 1, 2, 3 separate things that involve y's, which means that it would be a triple product, a product rule with 3 factors in it. What you can do instead is distribute the y inside the parentheses even though it would still technically be another factor, you've now kind of pared it down so that you're only looking at a single set of factors, 2 factors that you can differentiate using the product rule separate. All right, so we're looking at here, again, negative cosine comes along for the ride, cosine of y differentiates the negative sine of y. The 2 negatives cancel, so we're looking at cosine x sine y. Then minus, and then again, we're looking at a product here, e to the xy. So first times the derivative of the second. So now with respect to y, two y becomes a 2. Xy squared, I only care about the derivative of the y squared, which is 2y. So plus 2xy plus my second function times the derivative of the first. So 2y plus xy squared. The derivative of e to the xy, this piece right here, would become e to the xy multiplied by the derivative with respect to y. Y goes to 1, it's only the x that comes along for the ride, right? And so at that point, you finished, and you pray to everything you believe in that you didn't make a careless error along the way, which I'm sure I did. But yeah, it's breaking it up and being strategic about how you apply the product. So if I have to find f sub xy, I derive from, right, yeah, exactly. So it's the next level in the process. All right. So when you look at something like number 5, you see that monstrous expression, the natural log of xy and all that good stuff. You see it saying f sub x xy. You could be strategic about it. Now that's actually the cleanest orientation. It's the cleanest orientation, or I'm losing the word here. Arrangement is what I meant to say. Orientation, I guess, works, but arrangement's a better word. And also, I was looking at my notes there, making sure I didn't make a typo there. It looks like everything is right. Right. So, yeah. So, finding the consistent second order partial with respect to x. So x first, then x again, before switching over to y is actually strategically the best way to handle this. All right. So f sub x, we're taking the derivative of a natural log function. Whenever you take the derivative of natural log, it's 1 over whatever's contained within the natural log. You make that look like a fraction. So xy times the derivative of the thing that's contained within the natural log, right? With respect to x, so x is the variable here. So that's just going to give us a y. Right? So the y's cancel, and that part of it just ends up being a 1 over x. However, consider this. properties of logs are still a thing. That ln of xy, you could write that before you even get started as ln of x plus ln of y. You know, product becomes a sum. In which case, when I take the derivative, the ln of x would be the only thing relevant because the natural log of y would go to a 0 anyway. So this would just become a 1 over x. And it might be easier that way. Right? The second piece, I'm taking the derivative. I have a constant multiplier. The cosine is going to become a negative sign. So this is going to become a positive 2 sine x minus y multiplied by the derivative of the inside of the sine function with respect to x. The only part that's relevant there is that x, which has a derivative of 1. So that's going to give me a 2 sine x minus y. And then the last piece is polynomial in nature. Again, derivative with respect to x. X has a derivative of 1. So it's really just going down to y squared. Right, so that's a little bit nicer. Right, I want to take the derivative again. So maybe I don't want to have this as 1 over x. Maybe I want to have it as x to the negative first power. So that when I take the derivative a second time with respect to x, the straight power rule, negative x to the negative second, sine becomes cosine, so plus 2 cosine of x minus y. Again, the derivative with respect to x is going to be just the x component, which is a 1. Derivative of x is equal to 1. Right, that y squared is going to 0 because it's constant. It doesn't contain an x. So that's going to 0, that's gone. Right. So then the last part of the process is to find the derivative with respect to y. So I'm now working off of f sub xx, differentiating that with respect to y. Right. So this part is gone. That's irrelevant. We don't care about that. It's only this part that matters. We have a constant multiple of 2. Right. Cosine goes to negative sine. Right? So negative 2 sine x minus y. Then we differentiate just the y term with respect to y. We do that in green for consistency. The derivative of negative y would be a negative 1. So this cleans up actually kind of nicely to 2 sine x minus y. Right. So you could have done that by finding the derivative with respect to y first and then x and x again after that. But this ends up being the most efficient way because you have consistency in terms of the type of differentiation that you're following. Mm-hmm. You can see, even for the easy problems, it's still a fair amount of writing. And I would say, in addition to the writing, it's a lot of like talking to yourself. It's like, all right, so what? All right, derivative of this. Okay, working with x here. I did y last time. Now it's x. You know, there's a lot of that going on. So what we're going to do now is actually start applying this. And dang it, formatting again. So this, that, just terrible. All right, so I don't even know what happened here. So it should be z is equal to f of ab minus t. And get rid of this garbage. Actually, let me wipe it out. See if it'll actually recognize it. No, not really. I'll just leave it as is. All right. So we're actually going to make use of the partial derivatives now, which is going to be a big journey for us. Right? So, so you get the whole suppose that f of x comma y has continuous first order partials, first partial derivative at AB. The normal vector to tangent plane AB is given as, you can see the model there, and then we have the equation of a tangent plane. Right. So a tangent plane, and also there's a variation of that, which I'll get to in a second. But a tangent plane makes sense to talk about in 3 dimensions because we talk about tangent lines in 2 dimensions. So it makes sense that we would find the plane that's tangent to a surface rather than just a line that's tangent to the curve. Right? Because you could have infinitely many tangent lines to a 3-dimensional surface at a point. Those infinitely many tangent lines would correspond to a plane. Right? They would live in the span that is created by the plane. Right? So that's kind of what we're moving towards here. So you can see the first example. You're finding the equation of a tangent plane in the normal line to the surface. Z equals x squared y squared plus 1 for all of these points. All right. So it's kind of a daunting sounding problem, but it's actually pretty straightforward. What we need to do is first find the partials with respect to x and y. Now z is also known as f of x comma y. So I'm finding f sub x related to this expression. All right. So it's very simple because everything that doesn't involve an x is treated as either a constant or a constant multiplier. All right. So x squared has a derivative of 2x. The y squared comes along for the ride, the 1 goes away. All right. The f sub y would be the same idea, except we'd be taking the derivative of the y part of it, which is 2y, bringing the x squared along for the ride, and the 1 goes away again. All right. So how did I know to do that? Well, if you look at the notation here for the tangent plane, let me just use a highlighter here. You can see we have the f sub x and the f sub y in there. All right. Same idea for the normal vector, f sub x, f sub y. Those are representing the first order partials. All right. So now we just have to evaluate those at particular points. All right. So, but what we can do is we can build a model first. All right. So the tangent plane written in the form of z equals, that's not really how we're used to writing it. We could write it instead as f. It's up to you. You can go either way with it. F sub x of AB times x minus a plus f sub y AB y minus b minus z is equal to f sub is equal to negative f sub AB. F of AB, sorry. It's the same, right? The reason why you might consider writing it like this is because in this format, you'd have all the x's and the x, y's, and z's on the left side and any constant values on the right-hand side. But it really doesn't matter because in the end, a plane is a plane. We're not asking for any kind of standard form here. Right, but what we can do is we can get it to a point where it's starting to look a little bit more general in the sense that it's related to this function, but it's also containing particulars related to that. Okay, so f sub x times x minus a. Well, I would need my a values, but I can actually start writing it in immediately so I have a model to work on. So 2xy squared times x minus a plus 2yx squared times y minus b minus z is equal to negative f of a comma b. All right, so I'm working off of this model here. You know, a slight variation of it. Okay. So the points that we're given are 1, 1, 1, 0, 0, 1, and 0, 0. Those are all ready to be popped in. Right? Now, that negative f of a comma b, that's related to this guy over here, substituting in the particular values for x and y. All right, so we'd be looking at, so at 1, 1, all right, brutal, 1, 1, I would be saying 2 times 1 squared times x minus 1 plus 2 times 1 squared again times y minus 1 minus z is equal to, and then I would evaluate this for a and b. So if I wanted to say f of a comma b, I could write it above it. It's really a squared b squared plus 1. I could write it like that, knowing that these are my a and b values. I mean, but either way, that'd be something you probably just crunch in your head, right? So you're replacing the x's and y's with 1s, right? So 1 squared times 1 squared is 1, plus 1 is 2. So this side, because it's negated, would be a negative 2. Then it's just a matter of cleaning it up a little bit. So 2 parentheses x minus 1 plus 2 parentheses y minus 1 minus z is equal to negative 2. 2x minus 2 plus 2y minus 2 minus z is equal to negative 2. We can add the 2's to both sides. So we're adding 2 2's, so we're really adding 4. So we'd be looking at 2x plus 2y minus z is equal to 2. All right, and so that would be one of the tangent planes. You say, oh, so this sucks. We're gonna have to do this again 3 more times. The other ones are actually a whole lot easier. All right, so now we could also write the equation of the normal line. It's not going to be difficult, but we'll do all that in one shot. All right, so because the normal line is going to have the normal vector, but it's also going to go through the particular points. All right, so like I said, we'll cross that bridge. All right, so at 1, 0. So if you think about what we're working with in our general model here, these coefficients are really the driving force behind everything. If the coordinate that you're given, you know, the AB value has a 0 in it in any capacity, all this stuff is zapping away. So it's going to make life a whole lot easier. Why is the equation for normal vector directly? Oh, so the normal vector, if you go back to what we talked about writing the equation of a line in free space, you have the parametric form, which is trying to figure out where I can put it. Equation of a line. You have the parallel vector, which is ABC. And so it's x is equal to, we have some starting point that we call x sub o plus t a, y sub o, I'm sorry, y is equal to y sub o plus tb, and z is equal to z sub o plus tc. Right? So if we were to take the derivative of this is our equation of a line. This derivative, since it's linear, and I'll just highlight what it would be. The derivative would actually be the parallel vector itself, right? Because the derivative of a line is that line's slope. And so if I take the derivative of each of these with respect to t, I can write it as x prime of t y prime of t and z prime of t. I get a, b, and c. And so we end up with that normal vector as being the derivative of the equation of the normal line. That's kind of a cool little relationship. So I'm just trying to figure out how I can kind of cordon that off a little bit. Good question. I like it a lot. I'm just going to chuck it in over there, then I'll go. There we go. So at 1, 0, this whole thing is going to boil down to just the negative z and whatever you get when you plug in a 1, 0 to the original function. All right, if you plug in a 1 for x and a 0 for y, the whole thing ends up being a 1. And so you get z is equal to negative 1. All right, so it turns out that any instance in which, for this particular function, in which either x or y is equal to 0, is going to kind of clean up very nicely. So at, let me do purple now, at 0, 1, it's going to amount to the same thing. Negative z is equal to 1, giving you z equals negative 1. Because again, these two pieces are going to zap away. You're just going to be left with this and this. Oh, sorry, they should be negative z is equal to negative 1 in both cases. So z is positive 1. And that's only because I forgot the whole thing is negative on the right-hand side. And then the last one at 0, 0. Again, zapping away, we're left with a negative z. Plug in a 0 here for x and y, you're left with a positive 1. Negated is going to give you a negative 1. So for each of these, you're actually getting the same tangent plane. All right, so that's kind of interesting to see that regardless of the situation, that we're ending up with the same plane tangent to the surface at that location. Right now, in terms of the normal line, right, so the normal vector is given as the partials evaluated at that given, or at whatever the value is, AB. So that's easy enough to figure out. So I can just kind of chuck that off on the side. Let me just shrink and move. You know what? Let me do that the right way. All right, so if I do f sub x at 1, 1, that result is 2. You know, it's stuff that we've already figured out, but I'm just going to kind of specify it all here. F sub x at 1, 0, and 0. f sub x at 0, 1, also 0, f sub y, f sub x at 0, 0, also 0. All right, same idea for y. So we're looking at this model really. All right, so f sub y at 1, 1, 2, and then 0 is the rest of the way. You know, there's nothing different. All right, so we have basically the ingredients necessary to come up with our normal vectors. In order to come up with the normal line, we just needed whatever the a value was and whatever the function is at that, I'm sorry, the a and b values and whatever the function is at those a and b values. Right? So to write the equation of the normal line, you know, just putting all the pieces together. So just chuck it in over there. So the vector would be 2, 2, negative 1, 0, 0, negative 1, and then the same the rest of the way. So you don't really need these formulas if you know how to write the equation of a line in 3 dimensions, because all you need is a point. And once you have the point, then you just need to put it in the appropriate linear form. Right? The fixed point plus t times whatever your appropriate vector is. Right? So it's really not that bad, but you know, it still takes a little writing regardless. So either way, let me just create a little more space so I can just kind of tuck it in underneath. I'll take it as a typo though for this problem. We definitely need like a full page of space. It's actually not as crazy as it could be because of the zeros in it, like the prevalence of the zeros kind of simplifies things a lot, but it still takes a fair amount of it. So I'll take that as a typo. So we just need to know what the y values are. I'm sorry, the z values are at the particular points, and we already kind of figured those out too. Right? So we know that if we plugged in a 1 and a 1 to the original function, we got a 2. Right? So I can actually make a little note of that. I'll just kind of tuck it in here. It was 2 for the first one and 1 the rest of the way. All right. So we have the A, B, and C values, right? Because those are, I'm sorry, I keep saying A, B, and C because, you know, it's A, B followed by C. The A and B values that they gave us for this problem, the 1, 1, the 1, 0, the 0, 1, right? And then the slope is determined based off of the partials at that particular location. Right? So let me resize again. Resize yet. I don't even know what the hell that was. So for the first one, and I don't know about you, but I prefer to write it as a vector value function. It just kind of makes it seem more reasonable. Those would be the normal line. All right, so And again, this is for the A values of 1, 1. Now, if you want, you can actually write it as an order triple 1, 1, 2. And I could just kind of tuck that in there. This is the same as saying it's the order triple of 1, 1, 2, 1, 0, 1, 0, 0, 1, 1, and then 0, 0, 1. All right, so this is the normal vector. We're writing the equation of a line, so this is the parallel vector. So we'd be looking at, I'll just color code it, 1 plus 2t, then 1 plus another 2t, and then 2 minus 2. So it looks something like this. So 1 plus 2t, 1 plus 2t, 2 minus 2. Then we'd have same idea. I can color code it right on down the line, I guess. So then the next one would be 1 plus 0t, so 1. Then 0 plus 0t, so 0. And then 1 minus 2. 0 plus 0t, so 0. 1 plus 0t, so 1. And then 1 minus t. Normal lines. Then 0 plus 0t, 0 plus 0t, and 1 minus t. All right, so we get there. It's fair, like I said, a fair amount of writing, but it's not. I keep saying how not bad it is. It's pretty bad, but it's not as bad as it could be. But then again, that's like saying category 3 hurricane is not as bad as a category 4 hurricane. It's like, okay, well, it's still a hurricane. You know? It sucks. So number 2, find the equation of a tangent plane and tangent line to the surface. Typo. Tangent plane and normal line. To the surface at this location. Right. So for these 2 particular points. Now, it's going to seem like a lot of the same stuff again, but this is really valuable information because see at the bottom, notice what is the equation of tangent line. I'm sorry, tangent plane at extrema. Now, in this diagram, I mean, if you can make heads or tails of what's going on in that, by all means, like, go for it. The only thing that I expected people to notice, hopefully, is that there's some points there that have been indicated, and those points are consistent with the ones that were given. But here, it looks like there's pretty clearly a relative max. This looks like a relative or a local max. Right. Now, there might be a local minimum in there also, somewhere along the way. So let's take a look. I mean, we're still going to have to do the partials. So f sub x, and it ain't going to be pretty, but I'm going to rewrite this as f of xy is equal to the cosine of x squared plus y squared to the 1/2 power. Right, just to make it a little easier to chain rulify it. Right, so we're looking at now that 1/2 power that 1/2 power only applies to the argument within the cosine function. So it's not like cosine is being raised to the 1/2 power. It's only the x squared plus y squared that's being raised to the 1/2 power. So cosine goes to negative sine of all that stuff. You know, eventually. Then we take the derivative of all that stuff, which would be 1/2 x squared plus y squared to the negative 1/2 multiplied by the derivative on the inside with respect specifically to x, which is only going to make this the relevant piece. So 2x. Right. So when I look for my first order partial with respect to y, it's really all this same stuff, except the derivative of the inner function is going to be 2y rather than 2x. All right. Oh, so I suppose I could change my highlighting here. All right, so that's something. Now, when it comes to evaluating, remember we have our A's and B's here. So overuse letters. So here's the A, here's the B. If I'm evaluating this for pi comma 0, so f sub x pi comma 0, I can tackle the trig part of it first, I suppose. But I could also take a look at anything else and, you know, see if things are going to clean up in such a way that maybe life will be easier. Right. So that's actually going to draw my attention to the second one, or the second derivative that I have here, the first order partial with respect to y, because I see here that the y value is a factor, or y is a factor of the whole derivative, and I'll be substituting a 0 in for y. So this whole thing's going to 0, which is great. Now, for the other one, that doesn't happen with the x term over here, but if I do get into the trig of it, I'm looking at this, I'm replacing the x squared with a pi squared, the y squared with a 0 squared, so 0. Then I'm taking the square root of that, which is just going to be pi. Sine of pi is equal to 0. So one way or the other, both of these zero out, which is great. Right? So then I can look at it for 0, 0 as well. So f sub x is 0, 0. Now in this case, x is 0. The y is also 0, but x is 0. So we can look at that and say, well, the whole thing's going to 0 out. But now we got to be careful about, if we get there, this piece. Right, because I have x squared plus y squared to the negative 1/2 power. Right, so if I'm replacing both x and y with 0, yeah, all this other stuff might 0 out. That's wonderful. That's wonderful. But this part here is going to be undefined, right? Because I'm going to have 0 to a negative power. That's 1 over the square root of 0, right? So this one is going to be undefined, right? So f sub y of 0, 0, that's going to play out the same way because we're making the same substitutions. So in for the x and the y here, well, actually, my highlighting is a little off now. So in for the x and the y, I'm going to get a 0. So this is going to end up being undefined. All right. So we're looking for the equation of the tangent plane. It's definitely going to be a little bit more of an interesting chore when it comes to the undefined case. But when it comes to the zero case, that should be pretty easy. All right. Now what I can do is go back to my original function, f of xy. Again, it's the cosine, it's all that stuff. We'll just reproduce it over here. Eventually, you know. I'm going to evaluate, we'll go with the pi 0 first. Evaluate it for pi 0. If I plug in a pi for x and a 0 for y, it's the same idea as up here. It's going to be cosine of pi, right? Because pi squared plus 0 squared is pi squared, the root of which is pi. Cosine of pi is going to be a -1. And I can do it for 0, 0, which is going to give me cosine of 0, which is a +1. Right? So I got all the bits and pieces that I need. Now it's just a matter of writing the equation of the tangent plane. Right? So at the tangent plane, at pi 0, -1, right? Because when I plug in a pi and a 0, I get a -1. So that gives me the a, b, and the f of a, b values. All right, I can get that information right in. I also have my slope. So I can use either of the two models up here, whichever one I prefer, to come up with my my equation. All right, so let me just highlighting again. So the derivative with respect to x and with respect to y at pi 0, those are my constant multipliers of x minus a and y minus b. You see in both cases it's equal to 0. Right. So then we're looking at a -z is equal to -f of ab. Right. So -z is equal to -1, so +1. So z is equal to -1. Right. So what I'm going to do just very quickly is bring up GeoGebra, which I don't have up. I'm going to bring up the original function and say really quickly, do you know? All right, so it's z equals cosine of the square root of x squared plus y squared. Right, so that seems to be the reasonable portion of the function. We'll get, I'll zoom out in a second. So let's take a look at z equals -1. Now let's also get the point of pi, comma, 0, comma, -1. So let me close this out. Plane. Wanted the plane done. And, oh, I did just graph the plane. So at the point 1, 0, I'm sorry, pi 0, -1, it does look like, it's hard to see really, but it does look like this is kind of like a bowl of some sort, like a, oh, what you call it, the guac bowls, like when you get the tortilla chips with the salsa and the guac, You get one of those nice bowls. They put all the chips in it. In the middle, they have all the dips. You know, it kind of looks like that. So at the bottom, it does appear that that point that we plotted, or I'm sorry, it does appear that the point that we plotted is at the bottom of that, and that could be a local minimum. Right? It does look like it has a circular minimum point. It's kind of like if you drop a pebble in the water and it's a wave propagating out from the center. Right? This would be the trough of one of those waves. Right? So that seems to fit. Right? So that would be a minimum point. Right? F of 0, 0 should be 1. That's entirely possible. Let's see. Oh, yeah. I don't know why I wrote that. Thank you. Yeah, F of 0, 0 is 1 because cosine of 0 is equal to 1. Thank you. Thank you. All right. So then it kind of begs the question, how the heck are we going to write the equation of a tangent plane at 0, 0, 1? Right? Because we know that we have the x value, the a value, the b value, and the f of a, b values of 0, 0, 1. So looking at this model here, it's like, well, how am I going to plug in undefined? You know, you can kind of operate under these. I mean, some people like to look at it and say, well, 0 is going to cancel out the undefined part of it. But that's just not the case. Right? If you get undefined, it could mean that you still have a tangent plane. Right? So what's happening here is that at 0, 0, 1, and let's see if this will actually allow me to type something in. If not, and now we're type in 0, 0, 1. You got that point at the top of the mountain there. If I type in z equals 1, I got another tangent plane. It's hard to see, I know, but we do have another tangent plane that appears to be going through that point. All right, and that's on the high side. All right, so this one is more intuitive, but we would arrive at z equals 1 based off of whatever this value is here, and recognizing that if your first order partials are undefined or equal to 0, just like in Calc 1, that could mean that there's a local max or a local min. The problem is, how do you plug in undefined? You don't. Right? You just got to know. Right? So in that instance, if it's undefined for both f sub x and f sub y, and if it's 0 for both f sub x and f sub y, then you're dealing with local extrema. Right? So you have local extrema when f sub x is equal to f sub y is equal to 0. Also possibly when f sub x is equal to f sub y is equal to undefined. Yep. So yeah, you know, we won't even bother with the normal line here. I'll take that as a typo. Typo being the word of the day. And actually the notice part, well, I could even leave that. If z equals f sub a comma b, f of a comma b. Right? So the equation of a tangent plane at the extrema is going to be in the form of z equals f of a comma b. Right? But you would recognize that there is potentially an extreme value by finding the first order partials and setting them equal to 0 if they don't already tell you what the a and b values are, and also setting them equal to some undefined value to see if that can possibly give you an extreme value. Right? So definitely a lot to absorb here, because it gets a little on the crazy side. The last thing that I was going to point out, we're not going to actually do anything with it, is not this stuff, is related to extrema and saddle points. That's actually what we're going to get to next class, page 52. So what I'm going to ask you to do between now and then, really not a whole heck of a lot, just read this. All right, so all right, so read this before next class. It's gonna it'll make life easier if you at least have some familiarity with this. But you can see here that what I just talked about is related to the critical points. All right, so both the first order partials are either equal to 0 or do not exist. That gives you a sense of whether or not there's a saddle point, a critical point. All right, so read through that again. That's page 52. And if you want to try some problems after that, by all means. We will pick up with the chain rule next class. It's pretty interesting stuff. It's also pretty straightforward, but that's kind of the natural progression, is to get into some more complicated instances. Right. So yeah, page 52. Right. So that's where we're going to leave it for tonight. So let me stop the recording.